Curvilinear coordinate systems 10. A tokamak fusion device has a geometry that takes the shape of a donut or torus. Calculations for such a device are sometimes done with the toroidal coordinates shown in the figure below. So we have this r coordinate, theta coordinate, and phi coordinates. Okay. So that's with respect to the x-axis, and then we have this phi coordinate, which is on the xy plane. This is the major axis, and here we have the minor axis. Okay. The major axis of the device is a vertical straight line that forms the toroidal axis of symmetry. So that's the z-axis here. The minor axis is a circle of fixed radius capital R0 that passes through the center of the donut, so that's this circle. The position of a point is described by the coordinates r, theta, and phi. The coordinates r and theta are similar to a two-dimensional polar system aligned perpendicular to the minor axis. The coordinate phi measures the angular position along the minor axis. So as you can see here, this is our phi. Part A, make a sketch of the unit basis vectors for this toroidal system. Are these vectors orthogonal? Do they form a right-handed system? And part B, obtain expressions relating the toroidal coordinates to a set of Cartesian coordinates. Let's start with part B first. Okay. Now, from this figure, we can see that if this angle is theta and this is our r, the projection onto the major axis, the z-axis, will give me r sine theta here. So that's going to be the projection. So my first observation is that z is equal to r sine theta. That's the transformation. Now projection of r onto the xy plane, where I use the polar coordinates r and phi, remember, we're going to have the projection onto the xy plane, r cosine theta, so that's going to be the projection here, r cosine theta. And once I take the projection onto the xy plane, now I'm looking at the x-axis where I have r0, the radius, and then I have this projection. So this is my r0, the radius of the minor axis, the circle. And then I have this projection r cosine theta. So r0 minus r cosine theta is going to give me a radial distance with respect to the origin, but then I have to take the projection onto the x-axis because the angular position is given by phi. So I'm going to have, for the x coordinate, x, I will have r0 minus r cosine theta, which is the radial position on the xy plane, multiplied by cosine phi to have the projection onto the x-axis. And as for y component, I have to take this component here. So it's r0 minus r cosine theta sine phi. So I will have y is equal to r0 minus r cosine theta sine phi, the projection onto the y-axis. So we can summarize these equations here. X, the Cartesian x-coordinate is r0 minus r cosine theta cosine phi, because phi is the angle it makes, the projection on the xy plane makes with respect to the x-axis. Then I have y is equal to r0 minus r cosine theta, which is the radial position on the xy axis, multiplied by sine phi, projection onto the y-axis. And then I have z is equal to r sine theta, because theta is the angle with respect to the xy plane. So these give me the set of coordinate transformations. R sine theta gives me the projection onto the z-axis. R cosine theta gives me the projection onto the xy plane. And then I have, so when this is projected on the xy plane, this makes an angle phi with respect to the x-axis. Phi is the angular position with respect to the x-axis here. So it's r0 minus r cosine theta cosine phi for x component, r0 minus r cosine theta sine phi for the y component. Now, in part A, I was asked to draw the unit vectors. So if I change these r theta and phi coordinates by a small amount, I can see where the unit vectors will point. So if this is my r, this is going to be my r hat. If this angle is theta, this is going to be my theta hat. And if this angle is phi, then the tangential vector, unit vector phi hat, is as shown here. Now I have to find the relationship between these three. So here I have, if I consider r hat cross product with theta hat, r hat cross product with theta hat, using the right hand rule, my four fingers of the right hand point along r hat, curl them towards theta hat, the thumb points in the direction of phi hat. So r hat cross theta hat gives me phi hat. And what about theta hat cross with phi hat? So four fingers of the right hand point along in this direction, and then we curl them into the page in the direction of phi hat. Our thumb points in r hat direction. So we find that theta hat cross phi hat is r hat. And what about phi hat cross with r hat? Phi hat cross r hat. The four fingers point into the page in the phi hat direction. Then we curl them towards r hat. The thumb points in theta hat direction for the right hand. So this gives me theta hat. So what does that imply? The r theta phi combination, r hat theta hat phi hat, they are orthogonal to each other, and their cross products imply the set of coordinates are theta and phi in the toroidal coordinate system. This is forming a right-handed coordinate system. And I recognize that by performing this cross products, r hat, theta hat, phi hat, by using cyclic permutations, r hat cross theta hat gives me phi hat, theta hat cross phi hat gives me r hat, and similarly phi hat cross r hat gives me theta hat. So this is the positive direction, and using the right hand rule I can follow these cyclic permutations in order to get the answer for cross products. So therefore these unit vectors r hat, theta and phi hat form an orthogonal set, and the corresponding coordinate system is a right-handed coordinate system. So going back to the original question, part A says make a sketch of the unit basis vectors. Are these vectors orthogonal? Do they form a right-handed coordinate system? Now we can see that these vectors r hat, theta hat and phi hat are orthogonal to each other. Their cross products imply that r hat, theta hat, r hat cross theta hat is phi hat, theta hat cross phi hat is r hat, phi hat cross r hat is theta hat. So this forms a right-handed coordinate system. Now in part B, we were asked to obtain expressions relating toroidal coordinates to Cartesian coordinates. So if this is r, and theta is the angle with respect to xy plane, r sine theta gives me z. And if I take the projection onto the xy plane, r cosine theta gives me the projection onto the xy plane, but phi is the angular position with respect to the x-axis. So r0 minus r cosine theta. So first I go r0, that takes me to this circle, but then I go back r cosine theta for my position here. So that gives me my radial position. And the projection onto the x-axis, I have to multiply it by cosine phi. Projection onto the y-axis, I have to multiply it by sine phi. So this gives me the set of coordinate transformation equations between r, theta, phi and xyz Cartesian coordinates.